So if you're listening to this right now, maybe you're driving to work or just drinking a coffee, you probably feel completely fine. But you are currently housing a pool of chemical fluid inside your body that is, well, it's strong enough to violently strip calcified rust right off of industrial plumbing.
Yeah, it's actually incredibly corrosive.
Yeah,
If you were to somehow extract that fluid and just pour it onto a metal table, it would immediately start eating into the surface.
which is just wild to think about. I mean, welcome to the deep dive, everyone. Today, our mission is to decode this fascinating stack of translated chemistry textbook pages all about acids. Because, when we hear the word acid, we usually just picture
Like glowing green vats in a superhero movie, right?
exactly some cartoon villain's secret lair. But looking at these sources, acids are actually hiding in plain sight. They're in our refrigerators, they're in our medicine cabinets, and as we just mentioned, they're literally inside our own bodies.
All right, the reality of chemistry is just far more intimate than we give it credit for. And the sources we have today are great because they cover everything from, the underlying molecular magic trick that actually makes an acid, all the way to some really strict safety protocols.
Yeah, and we're going to get into some truly wild stuff later, like
Yeah.
chemicals that can dissolve pure gold or eat straight through solid glass.
Exactly. It's a really comprehensive look at these compounds.
But before we get to the dangerous glass-eating stuff, we kind of need to understand what an acid actually is. And to do that, we should probably start with the salad dressing sitting right in your kitchen.
Yeah, that's a perfect everyday example.
Because the text lists all these surprising everyday acids that you interact with constantly, like standard vinegar. The sources note that vinegar is actually an 8% solution of acetic acid.
Right, and that sour punch when you bite into a lemon is citric acid. Or if you're having a bowl of yogurt or, sour milk products, you're tasting lactic acid.
It's literally in our groceries. And it's in our medicine too, right?
Yeah. Oh, absolutely. The text specifically highlights how crucial acids are in medicine. It mentions boric water, which is just a solution of boric acid. And then there's aspirin.
Wait, aspirin is an acid.
Yeah, the translated notes use the regional brand name acylprin, but the active ingredient there is cetyl salicylic acid.
Oh.
So we really rely on these things all the time.
Okay, let's unpack this because I'm trying to find the common thread here. We've got yogurt, we've got headache medicine, and we have like heavy industrial chemicals. What actually unites all of these things?
Well, it all comes down to the molecular definition provided in the text. Basically, acids are compounds that contain two or more elements. But the defining feature, the crucial part, is that they hold onto a hydrogen atom.
Just one hydrogen atom.
Sometimes more, but they have to have hydrogen. But just having hydrogen isn't quite enough. The real magic trick, as you call it, happens when that acid hits water.
Okay, what happens in water?
It undergoes a process called dissociation. The molecule basically splits apart. The water causes the hydrogen to break off as a positive ion, a cation, specifically H+, and it leaves the rest of the molecule behind as an acid anion.
So it's kind of like a really dramatic breakup. Like the second the molecule walks into the room being water, the hydrogen just aggressively storms out the door and leaves its partner behind.
That is actually a really great analogy.
Yeah.
Yeah, the hydrogen just storms off. And the textbook gives specific examples of this breakup, like hydrochloric acid, which is HCl.
Okay, so that splits into
It splits cleanly into one H+ posication and one Cl- anion. But then you have something like sulfuric acid, which is H2SO4. When that hits water, the structure actually causes it to split off two of those H+ ions, leaving an SO4 2- ion behind.
Wow, okay, so we know these molecules split and they release these aggressive hydrogen ions, but how do chemists actually organize all of this? Because if every acid is just throwing off hydrogen, it seems like chaos.
Right, they need a system. And the sources show that chemists divide them into two distinct families.
Yeah.
And it's all based on one specific element, which is oxygen.
Just oxygen, that determines the whole family trait.
Pretty much. So you have the first group, which are the oxygen-containing acids. These are made up of hydrogen, some acid-forming element like sulfur or nitrogen or phosphorus, and of course oxygen.
Makes sense. And the second group?
The oxygen-free acids, these they don't contain any oxygen at all. It's just hydrogen paired with another non-metallic element, which is very often a halogen.
Okay, and the translated notes get pretty specific about how these are named, right?
Yeah, the naming convention for these oxygen-free acids in Czech is actually really strict. You start with the noun for acid, which is kyselina. Then you make an adjective out of the elements involved, and you always end it with the suffix ova.
Okay, so here's where it gets really interesting. Because you mentioned halogens, and the text highlights a specific oxygen-free acid that pairs hydrogen with fluorine. hydrofluoric acid, or HF.
Right, which is created by dissolving hydrogen fluoride gas in water.
Yeah, and the text says this stuff actually etches glass, like it eats right through solid glass. So my question is, how is something that literally eats through windows practically used in the real world, like without destroying the whole factory?
Well, it's handled very carefully with specialized equipment, but the amazing thing the source points out is that its glass-eating property isn't a side effect. It's precisely why it's useful.
Wait, really? We want it to eat the glass?
Exactly. It's used in manufacturing to create opaque glass. You know those frosted glass fillings you see on office doors or bathroom windows?
Yeah, of course.
They use hydrofluoric acid to intentionally attack and scar the surface of the glass to get that frosted effect.
Oh, wow, that is wild. But I mean, if an acid is strong enough to eat through a solid glass window, that has to completely change how you handle it, right? Which naturally leads us to the textbook's rules for acid safety.
Oh, absolutely. The rules are strict and non-negotiable. The text notes that many acids are strong corrosives. The term used is giravini.
Giravini. Sounds intense.
It is. These substances can severely damage skin, mucous membranes, your eyes, your respiratory tract, even your clothing. So protective equipment is just rule number one. You have to respect the chemistry.
Right. And that brings up the most famous rule of chemistry. I think anyone who ever took a high school lab class remembers this. The dilution rule. How you're supposed to mix acid and water.
Yes, the golden rule. You must always carefully pour the acid into the water. Never, ever the other way around.
Because the text states that diluting acids releases a massive amount of heat.
An incredible amount of heat, yes.
You know, it's kind of like, okay, think of it like easing yourself into a boiling hot bath. If you pour the acid slowly into a big tub of water, the water can handle the heat shock. But if you do it backward, it's like dropping a giant ice cube into a deep fryer.
That's a perfect visual. The water instantly flash boils, turns to steam, and blasts that corrosive acid everywhere. It's a localized explosion.
Which is terrifying.
It is. And this raises an important question, which the text thankfully answers. What happens if you make a mistake and actually get splashed by one of these corrosives?
Yeah, what is the first aid protocol there? Because panic is probably the first reaction.
Right. Well, the exact protocol from the source is to immediately wash the affected area with a heavy stream of running water. You want to physically flush the chemical away.
Just drown it in water.
Exactly.
Yeah.
But then the crucial next step is to neutralize it with a solution of baking soda.
Because baking soda is a base, so it cancels out the acid.
Yeah.
That's really clever. So now that we know how to safely handle a spill with baking soda, we really need to talk about the star player of these textbook pages.
Yes.
Because there's a highly versatile oxygen-free acid that kind of embodies everything we've talked about so far. Hydrochloric acid, or HCl.
Yeah, HCl is fascinating. The text explains it's made by dissolving hydrogen chloride gas in water. Now, if it's perfectly pure, it's actually a volatile, completely colorless liquid.
But the stuff you buy at the store isn't colorless, right?
Right. The technical grade you'd find sold in stores is yellowish. The notes refer to it by the name Solna. And make no mistake, it is a strong corrosive.
Right, and it has some serious heavy-duty uses. The text points out that in the chemical industry, it's a raw material for making plastics.
Yes, it's essential for that.
But then at home, people use it to clean metals and just completely obliterate scale, like that crusty buildup around your sink. Vodny common, the text calls it.
Yeah, vodny common. It just melts it away. But what's fascinating here is what the text says happens when you mix hydrochloric acid with another specific acid.
Oh, right. The gold dissolver. This part is crazy.
It really is. The text reveals that if you mix concentrated hydrochloric acid with nitric acid, specifically in a 3-to-1 volume ratio, you create something called Luchawka Karlovska.
Which translates to aqua regia, or royal water.
Exactly. And this mixture is so incredibly powerful that it can dissolve noble metals. It will literally dissolve pure gold and platinum.
Which is just staggering, because gold is supposed to be the metal that never reacts to anything.
Right, but that 3-to-1 combination is just chemically devastating.
Wow. And the text also briefly prompts us to mention a few of HCl's oxygen-free siblings, right?
Yes, just to give a complete picture, the sources list hydriodic acid, which is HI, and hydrobromic acid, HBr.
Yeah.
And it also mentions hydrogen sulfide, or sulfitic acid, H2S. The text notes that this is actually a solution of sulfin gas. and it's used as a specific reagent in analytical chemistry.
Okay, so we've covered a lot of ground. We've got glass-eating acids, we've got gold-dissolving mixtures, we've got industrial plastic manufacturing. So what does this all mean for the listener?
Well, this brings us back to the very beginning.
Exactly, the ultimate twist from the text. This exact same hydrochloric acid, the stuff that dissolves scale and helps make plastics, is currently sitting inside your stomach.
Right, which sounds like a medical emergency, but it's actually just human biology.
Mm.
The source provides the context for this.
Why do we have this stuff inside us?
Well, in the stomach, that HCl serves a couple of vital purposes. First, it literally destroys disease-causing germs that we swallow with our food.
It's like a chemical security checkpoint.
Exactly. And second, it activates our digestive enzymes, specifically one called pepsin. Without that acid, the pepsin wouldn't work, and we couldn't digest our food properly to stay healthy.
It's just incredible. So to recap this whole journey we've been on, we started with the mundane, right? The 8% acetic acid in our salads and the lactic acid in our yogurt.
Yeah, and then we zoomed in to look at the molecular breakups happening in water, where that hydrogen ion just storms off.
We looked at the terrifying glass etching power of hydrofluoric acid. We learned the strict rules of heat management, why you never pour water into acid.
We covered neutralizing spills with baking soda, and of course the sheer destructive force of aqua regia dissolving pure gold.
It's a lot to take in, but
Yeah.
I think there's a final, really provocative thought to leave you with, based on all these sources.
I agree. I mean, think about it. We just spent this entire deep dive learning that acids are powerful enough to eat through solid glass. They can dissolve pure gold. They can strip calcified scale right off of plumbing fixtures.
Yeah, they're incredibly destructive.
And yet, human biology has somehow managed to harness that exact same destructive chemical power. We literally house a pool of highly corrosive hydrochloric acid right inside our fragile bodies, just so we can digest our lunch.
It's mind-bending.
It really is. It challenges you to look at your own body not just as a standard biological organism, but as a genuine masterclass in extreme chemical engineering.
I don't think I'm ever going to look at my stomach the same way again. Thank you so much for joining us on this deep dive into these translated notes. Stay curious, everyone. And please, always remember to pour the acid into the water, never the reverse. Catch you next time.